So welcome back to our discussion of DB2 and the continuation of our exploration of how the querying of a wider table affects the query processing of a query inside PostgreSQL and now MonetDB. If you recall, for PostgreSQL, we have seen that querying a wider table led us into an exploration of the internals of the heap file pages of the 8 kilobyte blocks, and that we found there that the fields of one row are held in continuous memory inside such a page. And we termed this row storage. So PostgreSQL is a row storage system. MonetDB is a column store. So everything is turned like 90 degrees and we are expecting consequences there. And this is the video that explores the consequences of how querying a wider table affects MonetDB. All right. So this would be our point where we again switch from the disk-based to the RAM-based database system, from PostgreSQL to MonetDB. In this particular case, we stick with the SQL probe query Q2. So we are querying the 3-column table ternary and then request all three columns A, B, and C to be outputted. Okay, and of course we expect consequences for a column-oriented DBMS. Before querying a unary table, it was sufficient to extract the payload of a single but. A single but, or the tail column of a single but, was sufficient to hold the column values of a single column. Now we have to process the column values in 3 different columns, and that will lead to the processing of multiple column buts, of multiple column vectors in some synchronized fashion, we hope. So before we do that, let's switch over to the interactive terminal here and create that 3-column table ternary in MonetDB. First, let's start a MonetDB instance and let's talk SQL to it. Okay, so we can now talk SQL to MonetDB using the M client, the embedded N client in my editor here. And well, we are going to drop and then recreate table ternary. Let's do that. Okay, so there we go. And then MonetDB's variant of the insert statement, which differs slightly syntactically from the PostgreSQL version. Recall that we have to count up to 1001 here to generate 1000 rows. The generated value is being referred to by the name value here, so that's fine. We have to use the log10 function to generate logarithms to the power of 10, but all of these are just minor syntactic details. So let's do this and generate all the 1000 rows. 1000 affected rows, that looks good to me. Okay, and then just for good measure, let's just execute the probe query Q2 here. So let's do that and see that the result looks as we expected from the viewpoint of SQL. There you go, it took some time. Okay, so there you go. This is a 1000 row table. It has 3 columns as we expected. This is the logarithm of by base 10 of 1000. It's 3. That looks good to me. Okay. And yeah, so I think it's time to simply explain that query. Have MonetDB reveal the internal plan of how such a query will be processed. Okay, so let's do that. Here's the plan. So let's make this a bit larger, so we can large postfix dump of information here, of timing information, and we'll come to that in due course. But this is the mul program. It looks a bit longer than the mul program for the unary probe query, for the Q1 probe query. But we see well-known but mul instructions here. So we see the initialization of the SQL subsystem of MonetDB. Okay, and then we see accesses to butts. This would be the butt that holds visibility information, if you recall. So this butt is just called this ternary, just like the table, and it holds visibility information. Which of the rows of table ternary are currently in fact visible and have not been deleted, for example, by SQL delete DDL statements. Okay, and then there is more accesses to butts, namely access to a butt of doubles, as you can see, a butt of doubles, which represents the column C in our ternary table. So we have to access this particular butt. We have to access a string butt, which represents column B, and we have to access another individual int butt, which represents the column contents of the column A of table ternary. So as expected, we have to access a number of butts here. The visibility butt plus one butt, one individual butt for each of the column contents of the individual columns of table ternary. Once we've done that, we are almost done with the processing. We will come back to this algebra projection statements in a minute, but what you see here, this large trail of mul statements, is just the preparation of a proper presentation of the final result of the query to the application or to the user. So all of this is preparatory work so that in the end we can fire this SQL result set, a mul statement, which will really assemble a ternary result table, a 3-column result table from the individual butt results that we have computed in this mul program. So that's how it goes. Lots of butts involved in processing this one particular query. So this would be the gist, this would be the core, the excerpt, the relevant excerpt of the mul program that implements query Q2. So we find the initialization of the SQL subsystem here. That looks good to me. And then the access to the visibility butt. Okay. And the access to all of the column butts, the C, the B, and the A butts, of course, properly typed as we've just seen in the real mul output. Once we have accessed the contents of column C, you will find that this algebra projection operation refers back to table C5, to butt C5, which holds the visibility information, and this algebra projection mul function will take care of removing all non-visible or deleted entries in the butt for column C. And you see that this happens again and again for the B and the A column butts. So all of these butts undergo algebra projection, all with the same visibility information. C5 is the butt that contains the visibility information. In all of these 3 butts, rows that would have been deleted before by the SQL user would be removed because they are invisible now. We have talked about this algebra projection operation and the role of it in removing invisible data from butts before. Okay, so once we've done that, you can see that what we've projected out of the A butt and what we've projected out of the B and C butts, all of these butts, they are input to the SQL result set function, which is then used to present a 3-column result to the user of the SQL subsystem of MonetDB. So a 3-column result will be collected, or will be assembled rather, from the 3 butts that really contain the column values. So all of this is a consequence of MonetDB's column-oriented orientation or column-oriented storage of table contents. So the view of the SQL user, would be this view. We are talking about table ternary, a 3-column table that is understood like this. So this is the first row with its A, B, and C values. This is the fifth row with its A, B, and C values. This is the n-ary view of tables that we are used to. This is the n-ary storage model, or the NSM in a sense. It's the default, the canonical, the classical view of tables. Inside MonetDB, we are to the right of this dashed line. And inside MonetDB, we implement the decomposed storage model, the fully decomposed storage model, or DSM. And the contents of this n-ary table here is represented in n binary tables. The wider the origin table becomes, the more binary tables, the more buts we have to use inside MonetDB to represent the same information. And you see that each of these n buts holds the contents of one particular column of the original table. All the A values collected in this but, all the A values are of homogeneous type tau1, so that makes sense. All the B values, all the C values in their individual buts. To present this n-ary view, this wide view of the table again, these individual buts are synchronized on their head columns, on their OID, or actually void columns, if you recall. So all of the entries that agree in their OID, which is 2 in this particular example here, all of the entries, individual buts that agree on their OID column, make up for one original row in this wide table. So taking these three together would be a representation of the row, which is not really present in MonetDB, with identifier with OID 2. Okay, so there is some reassembly work to be done to take these n individual buts and reassemble their contents, the tail contents in this particular case, to recreate the original n-ary table that is visible from the viewpoint of the SQL users. So this is really one very important aspect that tells PostgreSQL and MonetDB apart. In PostgreSQL, we've been living in the row storage world, where the storage, so the bits that are really continuous in memory, are oriented row-wise. So 1, 2, 3 would be continuous in memory, and that means the fields of a row, of a single row, are continuous in memory. In the MonetDB world, we are in column storage land, and if 1, 2, 3 are continuous in memory, then we see that actually the values in a single column are continuous in memory. Okay, so everything has indeed turned by 90 degrees. What has been rows before becomes columns now when it comes to storage. Accessing the same fields in one row is very efficient in Postgres, because we are guaranteed that all of these bits are assembled together very closely in memory, maybe even in a single cache line of your CPU. Accessing the values in a single column in MonetDB is very efficient, because these column entries will be continuous in memory, or maybe even inside a single cache line of your CPU. Okay, both of these models can have advantages and disadvantages. Recall queries, or imagine queries of the form select t.star from table st. T.star really requests the outputting of all columns of all fields of a particular row, and this row storage format really supports this quite efficiently and quite well. In the same way, t.star requires much more effort from a column-oriented database system, because t.star would require to collect the values 1 and 4 and 7 here, and these might not be in continuous memory. They might be in different cache lines. One might have been loaded from disk already, the other two might be not in RAM. So there is some effort involved here. But if your query is something like select t.a from table st, then the column model looks really efficient because it really can only load the content of this one particular column A. This is all that would be needed to respond to a query that requests the t.a column only, and we would not waste cache memory or not waste any time and resources to even bring in the B and the C columns. This is different in the row storage world, where we would bring in the B and the C values regardless of whether they are needed by a particular query. You see that this slide is talking about OLTP and OLAP here. So OLTP is an abbreviation for online transaction processing. This is a type of query that often contains clauses of the form select t.star. And such queries are better handled or appear to be better handled by row storage. OLAP queries, online analytical processing, often visits all entries, all values in one particular column of a table to compute statistics or other aggregates, and it appears wasteful to bring in from disk all of the non-reference columns like B and C if we are only referring to t.a in such an aggregate. In this case, the column storage of MonetDB seems to be of advantage here. So there's no clear winner and no clear loser in this game. It's a different design decision with really far-reaching consequences. So inside MonetDB, we will have to perform a join between these three binary tables or buts to reconstruct the original three column wide row of the original table. And reconstructing an original row of n fields would require us to evaluate n-1 equi-joins between n-1 n buts. And of course, the join predicate would refer to the head values. Those entries in these buts which share one particular head value would have to be considered together, and we would have to perform an equi-join on the head values to really bring the individual column entries together. This is quite an expensive operation, so the equi-join, or any join actually whatsoever, is among the most time-consuming and most pricey operations that a relational database system can perform for us. That sounds like bad news for MonetDB. Even a simple query like select t.star from table st would require us to perform joins internally to bring together, to collect together, to assemble together the row information from individual buts. But this is not the case in MonetDB. If MonetDB splits up information of wide tables into individual buts, we can count on the head columns, on these void-carrying head columns of the participating buts to be synchronized. All of them will be of the same cardinality. All of them will start at the same sequence base offset. So a positional scan, a scan from top to bottom in all of these three individual participating buts will visit the entries in these buts in the correct order. Buts, as you recall, are ordered column vectors, are ordered data structures. It makes sense to speak about the scan that is starting at this very first row and then continues down these buts. If we do such a scan in synchronized fashion in all of the participating buts, the scans will hit the rows, the column entries AI, BI, and CI that belong together in the white table at the same time and can reproduce them at small cost. Okay, so actually this operation, such sequential coordinated scans, is something that you can also invoke in mul. It's something that you can see when you, for example, use IO print, the mul instruction IO print with more than one argument. An IO print with more than an argument will scan the but arguments that you supply here, maybe 2 of them, 3 of them, more of them, in a synchronized fashion, just as we've described here, and will perform a very efficient very cheap positional join, I would call it. A join based on the position of the rows in these individual butts to reproduce the wide result that we need to see. So we can demonstrate this here over here in the interactive system. So let's just quit the SQL speaking M client here and instead invoke a mul speaking M client. Okay, so you can see that the prompt has changed. We can now talk mul to this particular system. And if we now replay the core of the mul script that we have just seen, the plan for the probe query Q2, then we would see this sequence of statements. We would initialize the SQL subsystem, and then we would perform the required but accesses and the projections that we have just talked about. We would access the visibility information, and we would of course access the three individual buts, B and C here. Okay, once we've done our projection to apply the visibility information to the three individual buts, we would have resulting buts A, B, and C that carry the final information that we want to print. And as you can see, I'm using the multi-argument version of IOPrint in this little mul script that will perform a positional synchronized scan of the three buts here, of the A, B, and C buts, and then reproduce column entries that really belong together and make up one whole row. Will scan these column entries and output them together to form a wider row of information. So let's see how that looks. Let's run the whole thing in one go. Okay, it takes a while. Okay, there we go. There we go. So this would be the output of IOPrint, and you see that we indeed see the synchronized output of the contents of the three participating buts of the A, B, and C buts. We also see the head, the void entry on which these the entries in the buts A, B, C have been positionally joined, and you can see that this synchronized scan of the three buts has produced all of the necessary information that we would need to produce the three-column result to our original SQL query Q2. Okay, so more is involved to process such wider tables and to produce results that have more than one column in MonetDB, but it's still efficient. We can count on synchronized buts that are synchronized in their head columns, and we can use positional scans and positional joins to do that. All right. Okay, so much for that. That's quite interesting already, I would say. It really brings in front a very fundamental difference between PostgreSQL and MonetDB already. There are many more such interesting differences between the two systems and the implementation approaches, but this is a story for the upcoming videos. I hope I can see you then. Bye-bye.